Hello, I welcome you all to this another interesting screencast. The problem reads the sports car is traveling along a 30 degrees banked road having a radius of curvature of rho equal to 500 feet. If the coefficient of static friction between tires and the road is mu s equal to 0.2, determine the maximum safe speed so that no slipping occurs. Neglect the size of the car. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Hibbeler. So let's draw the free body diagram. Let me just remove this here and then so that I will draw it separately, which I've done. There we go. Right. So what do we have? Maybe I move it somewhere here. So to start with, we do have the friction. I mean the weight. The weight, let's say, is acting through the center of gravity and it's vertical like that. Not sure this color is good. Let me try blue. It's not good enough. Contrast, maybe green. Alright, there we go. So that is our weight. This is W, our weight of the car. What else do we have? We have the friction. It's in this direction like so. We do have the friction in that direction like so. Alright, we do have the normal force. Right, like so. Okay. What else do we have? So we have the weight, we have the friction, we have the normal force, right? So now we need to write this in terms of our coordinates, components. All right, let me just draw this to just show that this angle here is 30 degrees. So this is 30. So if this is 30, then we know that this angle here is 30, right? This is 30. This is 30 degrees. And this angle here also. Okay. So if this is 30 there, this will be 60. Therefore, this will be 30. Agree? Okay, let's go. Let's write this. So this is 30 also here. Okay. So there we go. So let's write down these components. Like I said, this is the friction force here, which is Fs. Okay, and then this is the normal force. All right. So the friction force will have components. We are going to have one component in this direction like this. We'll have one component in this direction like so. Okay, and then we'll have another component. Let me just make this a little bit short. We'll have another component in this direction like so. Okay, so that is, we are going to call this as Fs cos 30, and then this one is Fs sin 30. The normal force, we are going to have some components also. Normal force, we have one component in this direction. and another component in this direction. Alright, this components, this one is just going to be equal to n cos 30, and this one will be n sine 30. Alright, I guess we are done. So this here is our n. This here is our n coordinate. Okay, this is our n coordinate. Alright, so this is our n coordinate. Let's call this as n, and then this one is our b coordinate. Okay, let's call that our b coordinate. Of course, we are not going to have any motion along the b, but along the n. Along the n, we are going to have some acceleration there, centripetal, and so on. Alright, so let's sum up. Let's apply the equations now of motion as well as of static equilibrium along the b axis. So we'll say summation of forces along the b is just going to be equal to 0, going up in a positive reference. So what we have along that direction, we do have n cos 30. Okay, what else we have? Minus w minus fs sine 30 equal to 0. Alright, and we know that our fs is nothing but equal to mu sn, which is just equal to 0.2 n. So writing this, we're interested in the n, so we are going to say our n cos 30 minus, we also know that w is nothing but equal to mg, right? That's our w is equal to mg. So this is mg, w is equal to mg, right? Then minus, minus 0.2 n sine 30 equal to 0. So factoring out the n, our n will just be equal to mg, right? Our n is going to be equal to mg divided by cos 30 degrees minus 0.2 sine 30, right? Okay, right. So there we go. We have found our n. Okay, so now let's apply the other equation, the one that we are going to use to find the speed along the n. So say summation, this is the equation of motion because we expect motion in that direction. Summation of forces in the n-axis in this direction being our positive. So our motion will be in this direction like so, calling this as our MAN. So this is MAN. So what do we have in that direction? We do have Fs cos 30 plus n sin 30 equal to, this is equal to M AN, where AN is just the centripetal acceleration. This is rho v squared over rho, where our rho is given as 500 feet. Okay, so writing this, we are just going to have this Fs we already computed it is 0.2 n cos 30, then we have plus n sin 30 equal to m v squared divided by rho. Right, so let's make our v squared subject of the formula. Before we do so, we can factor out the n here, I think so. So let's factor out n. So we are just going to have 0.2, there we go, cos 30 like so, plus sin 30 equal to mv squared divided by rho. Let's plug in this n there. Let's replace this n with this n here, and once we do so, then we are going to have the following: mg divided by cos 30 squared, cos 30 degrees minus 0.2 sin 30, then times 0.2 cos 30 plus sin 30, then equal to mv squared divided by rho. We can cancel out the m there and there, and right, let's just create some space this side. So let's write this equation in terms of v squared. So we are going to have v squared is equal to rho times g, then times 0.2 cos 30 plus sin 30, then divided by cos 30 minus 0.2 sin 30. Okay, our rho is equal to 500 feet, and our g in feet per second squared is 32.2. Alright, squaring both sides, we are going to have our v, which is our v maximum. We'll have our v, which is v maximum, and this is equal to plus 0.2 cos 30 plus 0.5 divided by cos 30 minus 0.1 by 500 by 32.2 square root of that. So our Vmax is just 118.95 feet per second. Okay, this is let me just write the units. This is feet per second. So this is the maximum self speed that our sports car can drive, so that there is no slipping that occurs. Right. I guess this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and I'll see you in my next screencast.